All right, so we worked hard for a couple of weeks, and so we get a 3-day weekend. All right, so don't come on Monday, but remember that the assignments are still due on the normal time, right? So by 10:30 a.m. on Monday. Next UTF is on Tuesday. SI, UTF starting next Wednesday or continuing. Okay, so we have been talking about proton NMR. All right, so we talked about the basic kind of theory about how signals are generated. We talked about chemical shift. We talked about integration. And last time we started talking about splitting. Right? And remember, splitting is what happens is when we have protons on a carbon adjacent to a proton that we're observing. Right? And those protons on the adjacent carbons can split the one we're observing, and the general rule is they split it in n plus 1 peaks. Right? So if we have 3 protons, we have a methyl group next door, 3 plus 1 is 4, it splits the peak that we're observing into a quartet. All right, so we went through and we put up a number of examples as well. So today what we're going to do is we're going to look at a little bit more splitting, a couple of examples of some more complicated splitting patterns. We're going to work some examples, and then we're going to talk about C13 NMR. Okay, so we're just going to add one more technique on top. All right, before we do that, let's do a quick clicker question. Okay, so yesterday we finished by talking about splitting patterns. Right, I had another slide that showed. Okay, let's stop talking, please. That I showed some pairs of peaks together, but the main thing is that we see this n plus 1 in the splitting patterns. And one example I showed you, I drew out this peak for this middle proton on propane, 2-bromopropane, right? And we said that proton would get split by both of the methyl groups. So there were 6 equivalent protons, so we did 6 plus 1 is 7. And so we said we would see a peak that looks like this septet right here. Okay? So let's look at the spectrum of this compound and see if that's what we actually see. Okay, so here's the proton NMR spectrum of 2-bromopropane. All right, so we see at the upfield side, this is for HA. Notice that HA is labeled for both of the methyl groups. So they are both observed within the same signal. But what about the splitting? What kind of a pattern do we see? It's a doublet, right? So that signal is getting split to a doublet because both of the methyl groups have a single proton HB on the adjacent carbon. Okay? And then HB, like I drew out on the previous one, here's the signal for HB. So it has 1, 2, 3, 4, 5, 6, 7 peaks, septet. Okay? So just like I drew it. Yeah, question?
Does the ratio between the 2 separate signals tell us anything about how many protons are on each carbon?
Absolutely. So the question was, does the ratio between the size of the 2 peaks tell us anything? And they don't. That data isn't shown on this spectrum. But if we saw an integration, then should be the area of the ratio of the what should be the ratio of the areas under those peaks? It should be in a 1 to 6 ratio, right? If we measure the integration. Okay? All right, so let's see what I got. Oh yeah, we skipped this one. So the sizes of these coupling constants, the amount that's being split, we're not going to talk about too much, but there is one situation that can be particularly useful to know some different coupling constants. And that has to do with protons on double bonds. Okay? So the splittings, so in each one of these double bonds we have 2 protons, but they have a different kind of geometrical arrangement in each case. Okay? In the one on the left side, we have both protons on the same carbon, right here. HA and HB, when they're on the same carbon, we call those protons geminal. That's their relative relationship to one another. Now the size of the splitting, the coupling constant for geminal protons is between 0 and 3 hertz. Okay, so it's very small. Okay, they don't split very much when they're on the same carbon. If those protons are on the same side of the double bond, or they're cis to one another, the size of that coupling constant goes up to between 5 and 10 hertz. And if those protons are trans to one another, the coupling constant goes even bigger. So between 11 and 18 hertz. All right, so in a spectrum, if we see that there's a double bond and we can measure the distance between the peaks, this coupling constant, we can identify their relationship to one another. Okay, so for example, if we had some molecule like this with a trans double bond, or if we didn't know if it was trans or cis, if we could measure the coupling constant, we could tell which of those arrangements or which of those stereoisomers we have. Okay, so this is a particularly useful type of situation. Okay, so coupling can become more complex than what we've seen already, and it can get what we might call. Oh, did I skip? What I showed on this next one is some more complex splitting. Okay, so what can happen is if a given proton splits to more than one different type of proton, to non-equivalent protons, then it can be split by one into some kind of pattern, and each of those peaks will be split again from the other side. Okay, so let's just set up a scenario here. So let's say, based upon what we saw in the last slide, that the coupling constant between A and B, so sometimes we go J, A, B, so that means it's the coupling constant between A and B, let's make it 10 hertz. Okay, so that was in the range that we were given on the previous slide. There's also a coupling constant between A and C. Okay, so this is the trans coupling. Let's say that that's 15 hertz. And then the last coupling that we might see here is between B and C. So this is the geminal coupling. And so let's say this is 3 hertz. Okay? So notice that each of those protons is involved in 2 different couplings. All right, so the way that we draw these is we draw kind of a tree, a splitting tree. It's kind of like a genealogy tree or something like that. So what we do, let's draw what the peak would be like for HA. Okay, and what we do is we start with a singlet. Okay, so that would be what that signal would be with no splitting at all. Okay, so I'm just going to start here with a single line. So here would be just a singlet. All right, and then we're going to split it by one of its couplings, depending on the coupling constant. So what I always do to make it easier, you don't have to do it this way. You can add these up in any order you want, but it's easier to do the bigger splitting first. Okay, so notice that HA has these 2 coupling constants, so 10 hertz and 15 hertz. So we're going to show a splitting for the 15 hertz first. Okay, so when HA couples to HC, what is HC going to split HA into? What kind of a pattern? Just a doublet, right? There's one proton that's HC, so HC n plus 1 splits it into a doublet. Okay? So we're going to split this into a doublet, some arbitrary distance here, but we're doing the big one first, and we're going to say that this distance is 15 hertz. Okay? So now, this doublet that we just generated can get split again by the AB splitting. Okay? And so we're going to split each of those now by 10 hertz. Right? So we know that on this first one it was split by 15. So, to go back to the middle would be 7.5, right? And if we split it by 10, it's going to be 5 on each side. So it's not going to quite go back to the middle. So this is going to go kind of like this, and this, and this. Okay, so we'll say that this is 10, and this is 10. And because they're all doublets, their intensities are just going to be 1 to 1 and 1 to 1. Okay, so what the signal would look like would be just something like this. We'd have 4 peaks, all roughly the same height. Okay, if we just saw this and we tried to measure the distances, what we would see is, right, this is 10, just like I have above, this is 10. From here to here would be 15, or from here over to here would be 15. Okay, that's where you'd find the second coupling constant. Okay, and so because there's 2 doublets involved here, we call this a doublet of doublets. Okay, or we just go DD. Okay. Now, this is the easiest complex one we could have, a doublet of doublets. It could be a doublet of triplets or a triplet of quartets. It could be something very complicated. So let's just draw the other ones and see how they would differ from this peak. Okay, so we're going to draw the peak for HB now. HB has a 10 hertz coupling. AB is the 10 hertz. And BC is only 3 hertz. Okay, so if we do the big coupling this time, we're going to start with the 10 hertz coupling. And then the smaller one is going to be only 3. 3 and 3. So this is still a doublet of doublets, but the coupling constants are different. Okay? So this one would have the 2 like this, and 2 like this. It's not a very good drawing there, huh? So these would be 3 and 3. And this from here to here would be 10, and from here to here would be 10. Okay? So if we measured on these, and we could measure, this is 10, and then we found, this is 10 over here, and we know that these 2 protons couple with each other. All right? So they either have to be on the same carbon or adjacent carbons. Yeah, question?
So if from B to C that instead was 5 hertz, would we only have 3 peaks and the middle one would be taller?
Yeah, so that's a good question. So if we have, we can have combinations of these coupling constants where they kind of overlap, right? So right now we have this gap in the middle. So if the second one, the second one would have to be 10 hertz. 10, because if we have 2, if this is 10 and 10, and the second one is 10, then the middle one overlaps perfectly. Okay? And that's just like coupling to 2 equivalent protons, we get a triplet. Okay? All right, so let's look at the third one, HC. All right, and C has a 15 hertz. This one's 15 and a 3 hertz. Okay, so this would still be a doublet of doublets. But we kind of have two doublets that are far apart. All right, and so this one, this would be 3 and 3. And from here to here, this would be 15. And from here to here, this would be 15. Okay, because we have this 15 hertz gap, and we know that this one has a 15, we know that those two couple with each other. You know, this has a 3, and this one has a 3, so those couple as well. All right, so we can figure out which ones are coupling to which by measuring all those coupling constants. Yeah, question?
Just to double check, I think you've probably already gone over this, but I'm kind of unclear. How far away can two protons be in order to affect each other?
Okay, so the question is through bonds, you mean the number of bonds. Okay, so the most common situations are that they're either on the same carbon or on adjacent carbons. There are some situations where they can couple beyond that, but it's much less common. Okay? Remember that a very important part of this is that for protons to couple, they have to be non-equivalent. Right? So even if two protons are related by symmetry, even though they're next to each other, they become the same by symmetry, and so they don't couple with each other. Okay? So they have to be non-equivalent. Okay? So let's look at one consequence as well. If we just look at, or think about what the spectrum would look like for just one bromopropane. All right, a couple of these are pretty easy. So for the methyl group, what kind of splitting would we see for the methyl group? Okay, we just look at how many protons are on the adjacent carbon. There's a CH2 next to it, right? 2 plus 1. We'd observe a triplet for the methyl group. Okay, the other one that's straightforward, or in my mind at least, maybe you guys don't agree. This is all straightforward. The CH2 next to the bromine, what kind of a splitting pattern would that have? It would also be a triplet, right? Because it also has a CH2 next to it. All right? So now HB in the middle is a little bit more complicated because it could couple to the methyl group, right? So if it coupled to the methyl group, what would it split into? A quartet. So a quartet, and if it splits to the CH2 on the other side, it would be a triplet. All right? So if the coupling constants to the methyl group and the coupling constants to the CH2 are different, we're essentially going to see a quartet of triplets or a triplet of quartets. So let's draw out what that could look like. Okay, so this is going to be HB. So we're just going to make the two coupling constants different from one another. So I'm going to draw a big quartet and a smaller triplet. Or no, let's do it the other way around. That's the book has this one, and that's how it does it. So let's do the other way. Okay, so we're going to say that the triplet is a bigger coupling constant. Okay, so I'm going to split this into just a really big triplet. Okay, the middle peak of the triplet is right down the center, and then the other two are like this. And then we're going to split each of those peaks into a smaller quartet. Okay, and I'm just going to make them so they don't overlap, just to make this easier. So here's a quartet. It's going to be, here's a quartet. And here's a quartet. All right, so if we had one big coupling constant and one small one, we might have something like this. So each of the quartets, what's the ratio of peaks in a quartet? 1 to 3 to 3 to 1. Okay, so within each of these quartets, it should be 1 to 3 to 3 to 1. Okay? Now, the quartets are into a triplet, though. What's the ratio of a triplet? 1 to 2 to 1. So the middle quartet is going to be twice as big as the ones on the outside. So we have like a bigger quartet here, and then another small one out here. Okay, so essentially here to here to here, these peaks are the triplet, right? There's three quartets. And then within those, we have these quartets here and here and here. Oops, that's... Okay, so that's what you would get if the coupling constants are very different. However, because this is just an alkyl chain, right, we might expect the coupling constant between the CH2 and the CH3 to be very similar to the coupling constant from CH2 to CH2. Right? There's no reason why those are going to be very different. And in fact, what we oftentimes observe is because these alkyl chains, we know that those carbon-carbon bonds can spin, right? We talked about conformations and all that stuff last semester. So because they can spin, we generally just see averaged coupling constants here. And so what's going to happen is if the JAB basically at least roughly equals the JBC, then we can treat, even though they're non-equivalent, we can treat those non-equivalent protons as being equivalent. So we can say, well, there's 3 protons over there, there's 2 on this side, so we have 5. 5 plus 1 is 6, right? So if all the coupling constants happen to be the same, we should get a hexet, or I think, no, they had a sextet. Okay, so if those are the same, then essentially what we're going to see is this thing that looks kind of like this, if I can draw it. It's just symmetrical in the middle this time. Right? So this is a sextet. Okay, so that simplifies it if all the coupling constants are the same. And then if they were, not drastically different like that, they can be overlapping in different ways and be much more complicated. So let's look at the spectrum for this compound. And they didn't actually blow up the one we'd like to see, but here we have HC right here, right? It's the most downfield because it's next to the more electronegative bromine. Bromine's pulling electron density away from it, de-shielding it. Okay? On the upfield side is the methyl group, and we can see from this expansion that it's in a triplet, right? Just like we expected, HC is also a triplet. And then all they give us here is that HB in the middle is observed as a sextet, right? Just like we drew on the last slide. Okay, so we know the coupling constants are about the same going each way. And this is pretty much what we would see in just an alkyl chain. All right, we're just seeing these averaged values. All right, everybody with me? Kind of? See, the better it'll be. All right, so we've kind of done all this stuff. We're starting to interpret NMRs. We can predict splitting patterns. So now what we're going to do is we're going to talk about C13 NMR. Okay? Some added... Oh, no, first we're going to interpret some spectra and do a couple of examples. All right, so here, I know they're kind of small. Here's a proton NMR and an IR spectrum for a molecule that has a molecular formula of C5H10O. All right, so what's the first thing we should do? Degrees of unsaturation is, I think, always the best thing to do if we have a formula. Okay, so how many degrees of unsaturation do we have? 1, right? So remember, we can calculate it like this. Unsaturations equals the number of carbons, 5, minus the number of hydrogens divided by 2. If there was nitrogens, we would add the number of nitrogens divided by 2, but we don't have any, and then we add 1 at the end. Okay, so we have 5 minus 5 plus 1. We have 1 side of unsaturation. Okay, so we have to have a double bond or a ring. Okay, so let's just look at these spectra. We could look at the IR first and try to pick out some functional group. We need something to account for the unsaturation. All right, so what do we see in the IR? Notice that this IR spectrum only goes to 1500, so they're not showing us the fingerprint region. Yep, so we have this big peak right here at about 1700, right? And that's very characteristic of a carbonyl, carbon-oxygen double bond. All right, what would these peaks right here go to? Right, so this is the hydrogen, carbon-hydrogen stretches because it's below 3000. This is the hydrogen to sp3 hybridized carbon stretches. Okay? So we know we have a ketone. We have 5 carbons. So we have to figure out where in the molecule that ketone is. So now let's look at the proton NMR. Okay? What we see is that we have, what do we have? These expansions. So this one here, excuse me, is a doublet for 6 protons. All right, so they're telling us there what the integration is by the 6H above it. We have a singlet for 3 protons, and we have this complicated signal here for 1 proton. If we can try to count that, it'd be 1, 2, 3, 4, 5, 6, 7. Septet. All right, so what kind of pieces can we pull out of this spectrum? Yeah?
I think the septet's indicative of like a dimethyl group. I don't even know what to call it. But like,
You don't know what those are called? If we have a CH with a CH3 and a CH3 and something's attached, what do we call that? An isopropyl group, right? Okay. Don't chime up if you don't want to be made fun of. We can speed things up if I do that. All right, so we have an isopropyl group. Does everybody see that? We have a septet and a doublet, right? And it's in a 1:6 ratio. So this is like we saw for that 2-bromo propane. All right? So then what else do we see? That accounts for 2 of the 3 signals. How do we count for the last signal? Yeah.
If you have the carbonyl next and then the methyl on the very end, it would count more.
Right, so the other peak is just a singlet for 3 protons, right? So that means we got a methyl group, but it doesn't have any H's on the adjacent carbon. All right? So we're going to put our carbonyl. We know that we have a carbonyl here, and we're going to put a CH3 on the other side. All right? So we don't see any coupling across that. So this one is going to be a singlet. Because it's next to the carbonyl, it has this chemical shift of about 2.1 parts per million. Yeah, question?
I'm just a little confused on why does the isopropyl count for 2 out of the 3 signals?
Because the question is, why does it count for 2 out of the 3? Because we have a signal here for the methyl groups, and we have a signal here for the methine that's in the middle.
Oh, okay.
So those are the two signals out of the three, right?
Okay.
Okay, so then this methine signal here as well is next to a carbonyl, right? But it is a tertiary carbon, so it's going to be further downfield than the methyl group, right? So we see that signal, that's probably at about 2.5, looks like. And then we have the two methyl groups, and those are upfield. These are about 1.0 parts per million. All right? So it's, all the information is there, right? You just got to figure out how to put it. Okay, let's look at another one. Okay, C10H12O. All right, so how many unsaturations does this have? Calculate that out for me. Five? Is that right? Number of carbons, 10 minus half the hydrogens. 10 minus 6 is 4, plus 1. We have 5 sites of unsaturation. Okay? So what did I say about situations when we have 4 or more sites of unsaturation? Right, there's oftentimes a benzene ring. Okay? So can we confirm that by looking at the proton NMR spectrum? There's a lot of peaks there, huh? Whoa. Huh? Yeah, look at all these signals down here from about 7.5 to 8. Okay, this is the aromatic, this is the benzene region. Okay, and how many peaks? We have 5 of them. So that tells us that we have a benzene ring and it has 1 point of attachment, right? So there's 6 carbons, but there's only 5 hydrogens on it. So there's a phenyl group. Okay? Because it has to be attached to something else. All right, now what about the other signals? It makes it look complicated because they have these kind of expanded portions. But we have a triplet. We have something here. How many? 1, 2, 3, 4, 5, 6 with maybe a little. This, can you see that little teeny thing on the side? I would probably not pay attention to that because we don't see it on the other side, right? Because these multiplets should be symmetrical. All right, so we have 6 peaks. So we have this sextet. All right, and then we have another methyl group on the other side, and these are in a 2 to 2 to 3 ratio. All right, so we can consider all 3 of these signals together. Right, so what would that give us? Just a propyl group, right? CH2, CH2, CH3. So this is going to be CH2, CH2, CH3. All right, and we know that the methyl group is here because it's worth 3 protons. We know that this CH2 is here because it's in the middle, and so it has more coupling. That's giving rise to that sextet. And then this one is a triplet because it only has a CH2 next to it. So we know that on the other side of that CH2 there cannot be any hydrogens on the adjacent carbon, right? Because there's no more splitting. All right? So we have to somehow link these 2 pieces up. All right? So what's a good thing to figure out now? Right, well, we just want to figure out how many atoms we have left to use to link these together, right? So we've used up 6, 7, 8, 9 carbons. We have 1 carbon left over, right? We've used up how many protons? All of them, right? Because there's 5 protons over there, and there are 7 protons over here, so 12. We've used up all the hydrogens already. Yeah.
So I think we've used all 10 carbons already? Because we already know that there's the attachment to the ring.
6, 7, 8, 9.
We have 6
Yeah, but
and
we don't
9.
know what's attached to that.
Okay.
This is just like a bond to nowhere at this point.
But because that left CH2 can't be attached to anything with hydrogens on the left side,
Mhm.
you would know that would have to be attached to the oxygen, right?
Yeah, we got to figure out, well, if we only had the spectrum, we could say, oh, maybe that propyl group can just be attached directly to the benzene ring. Right? Because the CH2 wouldn't couple to anything on the benzene ring because it's coupling to that quaternary carbon there. It's attached to it. Huh?
And then there wouldn't be enough carbons.
Right, so we got to figure out what do we need, what's left over, right? So we have 6, 7, 8, 9 carbons so far, and we need 10. Right, so we've got 1 carbon still to account for. We accounted for all the hydrogens, and we have 1 oxygen to account for. Right, so what do we put in the middle? Just a carbonyl again, all right? So we're going to have this with a carbonyl and a propyl group on the other side. Okay? Everybody with me? Good? All right, let's do... I love doing these kind of problems. I always threaten every year that, those books of like crossword puzzles or Sudoku or something like that. You like to put it on the back of the toilet and use it whenever it's convenient. Keep threatening that I'm going to make this little book of spectroscopy problems. You can just set that on the toilet and practice those as well. Okay, so C9H10O2. All right, so how many unsaturations here? 5 again. All right, so what can we pick out of this on this spectrum? Again, we have these signals down here in the benzene region. There's 5 protons, right? So again, we have this mono-substituted benzene ring. Then how do we account for the rest? These are a little not exactly right on their abundances, but I would say this has 4 peaks, right? So this is a quartet. This is a triplet in a 2-to-3 ratio. So how do we account for those 2 signals? What kind of group gives rise to a pair of signals like that? An ethyl group. Right? The CH2 is the quartet because it has a methyl group next to it. The methyl group is a triplet because it has a CH2 next to it. Okay? So now let's do what we did last time and figure out how many atoms we have left over. Okay, so we've counted for 6 for the benzene, 6, 7, 8. We need 1 more carbon that we have to account for. What about protons? Do we need any more? No, we've accounted for all of those already. And we have 2 oxygens. Okay, so what kind of a functional group can we put in between there that makes up essentially a CO2 group? Like an ester, right? So this gives us 2 possibilities, though. We could have an ester that's like this, or we could have an ester that's like this. Right? We're putting in the ester either of two orientations, right? So we have two constitutional isomers that we could have. So which one of these is the right one? So what's the difference? Let's look at these two structures and pick out a part of the structure that's going to be different, that's going to show up differently in a proton NMR spectrum between those two. So which protons would be the most different in those two? Yeah, I would agree. I would say the CH2 groups, right, here versus here, right? Because in one case, they're on a carbon next to oxygen, causes a lot of de-shielding because oxygen is more electronegative. Over here, it's just next to a carbonyl. Right? So if we looked back, next to the carbonyl, this is probably going to be more in like 2.2 range. And next to an ester actually pushes it farther than what we saw for most oxygen. For alcohols and things like this, this is going to be, upwards of, 4 or something like that. Okay, so which of those two fits the data? The one on the left, right? Because we see this CH2 group at 4.35 or something, so we know by the chemical shift of that CH2 group it has to be next to oxygen. Okay? So if it was the other one, we would see exactly the same patterns, but the chemical shifts would be different. Yeah, question?
Would you also see a singlet on the one on the right?
On the one on the right, no, there wouldn't be a singlet because this is still a CH2 next to a CH3. Right? So we still have an ethyl group. All we have as far as proton, we have an ethyl group and we have a monosubstituted benzene ring in both cases. Okay? All right, so in just one introduction to C13 NMR, and we're going to have to cover that on Wednesday when we get back. All right, so C13 NMR looks quite a bit different. Okay? Notice, well, for one thing, we're only looking at the C13 isotope, right? So it makes this technique much less sensitive than proton NMR. We're only looking at a small abundance. The chemical shift range is huge compared to proton NMR. So instead of 0 to 12, this goes from 0 to maybe 220. Okay, so it's very wide. Usually we run the spectrum, and I'll show you a little how this works, where we use something that's called proton decoupling, because every carbon, C13, has a proton on it, and that proton can couple to the C13. Okay, but usually we do this decoupling, and so it makes all the signals singlets. Okay? And finally, the unfortunate thing here is that because of the way the experiments are run, we can't integrate the signals. We can't tell exactly how many signals or how many carbons are represented by each carbon. Okay? So we'll talk a couple of slides about this on Wednesday when we get back, and then we'll look at some more examples. I'll try to come up with some more examples for you to practice on side as well. And then we'll have to do radical chemistry, and then we have an exam coming up. All right? So have a good 3-day weekend.